All right, this is CNET 129S, and we're going to talk about application logic tonight, which is really just a lot of stories. This is the less mechanistic, less technical sort of flaws you can have, and probably more serious, just like, for example, the number one vulnerability in all security is always social engineering. The humans making mistakes is the most dangerous thing on your network typically, and the most difficult to patch. All the con men and social engineers that find ways to trick your people into doing something stupid. So just having logic that is wrong in your application is a serious sort of vulnerability, and you typically cannot find this with a vulnerability scanner or anything. You really need a human to examine the application and see if there is some way to misuse it. So there's just a few examples here of flaws found in the real world. For example, here you have Remember Me, like you do in many websites, and that sets a cookie. And the cookie contains some garbled information, encrypted or something. And in this case, it's an encrypted string including your name and so on, which is fine. But your screen name is also saved in an encrypted form in a cookie as screen name. And it turns out that they used the same encryption algorithm to encrypt both cookies. And this means you can control the screen name, so you can just create a screen name that has somebody else's username in it, and then put that in the other cookie and get into another account. So you copy the Remember Me cookie into the screen name cookie. And now you change your screen name. So you decrypt. You copy Remember Me cookie into the screen name cookie. The app decrypts it. Now you see it's Marcus, some IP address, some number, some other number. So now you change it to like admin1, and then run it back through to get log out, log back in, and now you're the admin. So this is using another part of the app as an oracle to break through the encryption. And you don't need to necessarily decrypt things, find the key or anything. You may be able to encrypt what you need to encrypt without knowledge of the key, like you did it here. All right, so to find this, look for things that are encrypted, not hashed. Substitute other encrypted values, try to find an error, this sort of thing. Another trick from your book that I've used a lot on Android apps is to make a very long screen name that's just A's, like 32 A's followed by more passwords I've done, and then see if it encrypts in visible repeated blocks. Anyway, then password change is very often the weakness. So you got a form for password change that asks for username, existing password, and a new password twice, which is what it usually asks for, and that would be fine. But consider the administrator app. The administrators have a form which can change a password without already knowing your existing password. And that might be fine too, but in fact it's the same function running both of those on the server side, and when it comes in without an existing password, it takes that as a clue that it came from the administrator. So this is once again the same mistake we've seen many times, where a developer assumes that the traffic coming in came from their page and was not forged with a utility like burp. So clearly you can just take a password change and then use something like burp to remove the previous password and send it in, and the app will now interpret it as a administrator account. This apparently really happened to AOL. So, as usual, delete parameters and see what happens. Missing parameters may not just always cause a rejection, they might cause interesting activity. And then another one we talked about in previous lectures before, if you have a multi-step process, another common mistake developers make is to assume that people have gone through these pages in order. So you put something in the basket, you finalize the order, you enter payment information, then you enter delivery information. But if you record these URLs, then you can go back, add another product, skip the payment, and jump straight to delivery. And it might believe that you must have gone through the payment step to get to the delivery step. Now, the right way to prevent this, of course, is to put a random hidden field in each one of these forms, which you verify, proving that if you're on step 2, you really did click on my page of step 1 that is customized for every user. We've seen that, and quite a few of the Web Security Academy challenges have that feature in it, the anti-CSRF token. One of the many ways you can prevent this. But, this attack is called forced browsing, where you just go through, you do not follow the steps the developer expects, you jump. All right, so skip stages, try doing a stage more than once, try doing them out of order, and so on, and see if you get interesting error messages or interesting results. So this one, you could had a complicated process of getting insurance. You would submit an insurance application, you submit basic information, the app computes values, then you get a lot of information, and you finally send this to a human underwriter. The human underwriter will then examine this information and decide whether you are qualified for insurance, and use the same app to make records in there, and it'll put it on a post request to update things. So the assumption is that each request will contain only the parameters requested in the form, and just like the previous one, they assume that you're using the pages the developer wrote and not using an app like Burp that lets you add extra parameters that are not there on the original form. So what you do is supply valid data at an earlier stage, but then override it with later requests changing the value. And the app does not notice that the value has changed and give an error message. It just accepts the new values, and this made it possible to steal information of other applicants. You could also purchase insurance at an arbitrary price, because you could replace the monthly premium after it's approved, I think. Replace the monthly premium. You could also force approval. The underwriter could set a parameter saying approved equals no, but the attacker can set them later, bypassing the actual underwriter. This is more and more examples of the same problem of an app assuming that the data is staying the way the developer made it and is not being changed by a malicious attacker, and believing data that came from the user's browser instead of just only believing data that's on the server copy. So, take parameters from one stage, change them at another stage, see what happens. All right. Then there's breaking the bank. You can register for online banking. You get some information, you send it to a back-end system, which then sends a paper application pack to the customer with a one-time password, and they thought it was very safe. There's personal data required, a one-time password is sent by mail, you then have to call in and authenticate to get your password. So it's stored in the database here, and the same data object is used for online banking and registration. So the trick here is log in with valid credentials, then go to the registration function and submit a different customer's personal information. The app will now override it, return to the main action. So this is a trick. You can go partway through the process, then change yourself to another user, then go back, and now it accepts you as that user. So I'm not getting the exact details right here, but this is a combination of the last few things, where you change parameters you're not supposed to change, and you do things out of order. So you manage to find a way to get into somebody else's account. So that's the fundamental flaw. You can write to the same application two ways after strict authentication, but when you're newly registering, you can write without authentication, and that's the problem. You have taken a high privilege activity that should only be possible after you have authenticated, and you've also permitted the same data to be written another way. So you could call this insecure direct object access. All right. And so here's another one. You have a business funds transaction, transfer funds between two accounts, but you can only transfer it up to a limit, $10,000, without getting approval. But the code looks like this. If amount is less than some threshold, return false. Any transaction that's too large will require approval. It will return requires approval. But the attackers, of course, transfer a negative amount. The negative amount will not be considered to require approval, but if the app allows you to use a negative amount is just a positive amount going the other way. So you move a negative amount from account A to account B, that amounts to moving a positive account from account B to account A. And I've been doing a lot of blockchain security, and this kind of thing happens a lot in blockchains. in smart apps. All right. And so here's more numeric. A lot of numeric limits are out there. You can only order these many items. You can only make bill payments up to your balance. You can only, your quotes are just affected by your age. And all these things can be affected by negative amounts, and in the world of smart contracts especially, ridiculously large amounts that wrap around. All right, and then famous one, I've seen this a million times, cheating on bulk discounts. Like you can mail out an online form and get a free prize, and you can just fill it out many times or repeat it many times, run it through Tor, that sort of thing. This is how people cheat on online surveys. This one here had a discount if you add a bunch of items together. So you'd buy 3 things all together, but then all you do is go in the shopping basket, get the discount, and then delete a bunch of items in the shopping basket, and it wouldn't notice and remove the discount. So you get the discount when you don't deserve it. Reminds me of a real-world one that people used when I was young. I had a Commodore 64, and people would get an external floppy disk drive that cost like $300. And when it broke, they would fix it with the Toys R Us fix. You take it to Toys R Us and turn it and exchange it for another with like a fake return. You would go buy one from Toys R Us, then you would take your broken one back as the return and get your money back. You know, it's just, essentially amounting to the same thing. All right, and here's another one. They're trying to prevent you from doing code injection, like cross-site scripting. People still do that? Yeah, okay. Okay. Yeah. You know, what they ought to do is they ought to verify the serial number of products you're returning, but evidently stores don't. Reminds me of a scam I was personally involved in restitution when I worked at the Federal Trade Commission under contract, where these guys had a scam where they would just advertise paper and toner and other office supplies, and they would sell it at a really low price, and you would pay for it, and they would just never deliver anything. And it turned out a lot of businesses would just not notice for months or years, and they just kept the money. They did that for a lot, and finally got busted by the government. Anyway, so that they're going to remove these characters by putting a backslash in front of it. So that would prevent these from being interpreted as special characters, but they forgot to escape the backslash itself. So if I do foo backslash semicolon ls to try to do a command injection, it will backslash the semicolon, but it will not backslash the backslash. So this will make the backslash into not a special character, so it will allow the semicolon to get through. This is the problem, as you mentioned before, with deny listing. If you try to list all the bad things, if you make any mistakes or overlook anything, that leaves a hole people can get through. Whereas if you just list all the known good things and block anything that's not on the known good list, that is much more likely to succeed. All right, and so you've got input validation. It's going to change all quotes to double quotes to try to stop people from putting in quotes and getting SQL injection. But there's a length limit, so you can see what's happening. Why do 2 backslashes allow it to get through? Because this backslash works because the backslash is a meta character, meaning it don't give the next character its meta character meaning. But this backslash removes the second backslash's meta character meaning. That makes it a literal backslash, so it no longer escapes this character. You see what I mean? Yep, you're backslashing the backslash, so it no longer functions as a backslash. That's why if you had included the backslash in this list, like you should have, then entering this would give you 3 backslashes, and that would work. The first one would escape the second backslash, and the third backslash would escape the semicolon. Yeah, good. So here you got a length limit, and of course, as you can see, all you have to do, so if you put an input like this with an apostrophe, it'll change it into double apostrophe, and that will not break it. This is being interpreted as a literal apostrophe. So what you have to do is put in something 127 A's followed by a quotation mark, and now when it tries to add another, the length limit will remove it, so you do succeed in breaking the syntax. You know, that's the problem with a length limit and a defense which involves adding another character. All right. So to find this, you can put in long mistakes, things like this, and see if there's link limits that can trim off some of these. Because remember, if you have a even number of apostrophes, it'll be different than if you have an odd number of apostrophes, so you could detect this sort of thing. And then there's a search function, so you can access information, but only paying subscribers can see it. An anonymous user can perform a query to see what's there, but they'd have to pay to read the articles. All right, so you can't. The idea is that you cannot get useful information. The document titles are cryptic like this. But this is sort of like blind SQL injection. The query searches the full text of the documents. So if you guess, you can gradually trace out the data in there. Like you'd see here, I look for this, and then I try share issue, zero matches, dividend. If I guess words, I'll eventually find a match. So you can guess the contents. I still don't understand how an extra backslash can add in code. All right, let's go back to that. So Joe, tell me if I understand your question. An extra backslash. So this one here, the semicolon will be allowed. Semicolon will have its special meaning of separating two characters. But this one, this one will work. This one will not let you do command injection. So if this is like the ping form we did, where I put in something and then a semicolon and another command, if the attacker enters a backslash and the application converts it to this, then the ls will be executed. Is that okay? Why is the application converting that to that? That's what the defense is. See, the ping form that we used just let you put in this, foo semicolon ls, and then the ls would be executed. So that's the unprotected form. So the application is trying to prevent this attack from working. So the way they do it is anytime you have a special character, it adds a backslash before it. Now, this line of code will not execute the ls. The semicolon will be interpreted as a normal character, and it'll look for a command called foo semicolon ls. It won't do the ls. That's what's called escaping. This is a very common defense. You escape special characters by putting a backslash before them, and now they are treated as just characters to print, but not special characters. The problem is this is treated as a special character, and this is treated as a special character. The two that are safe are this one and that one. So if you backslash a special character to protect your application, you must also backslash the backslash. Exactly. If you backslash the backslash no longer is treated as a special character, but just something to print, so it no longer prevents the semicolon from being treated as a special character. That's the trick of escaping. Yep, that's it. Glow's got it. That's why this one fails. This one and this one would fail. And the reason why they mention this is because there's a thing called MySQL escape, real escape, something like that. There's a common function people use which adds the backslash, and a lot of people put that in and they say, there, it's safe now. And that's not as true as you might think it is. Yes, the application code is adding a backslash before any special character on this list. These are the special characters, semicolon, pipe, ampersand, and so on. But they forgot to put backslash on this list. So these are the characters that they thought were dangerous, and they backslash all them, but by forgetting to backslash the backslash, then this injection will break it. And you'll do this in the Web Security Academy. You'll see a lot of these ones with some defenses. Okay, now let me clean this slide up so I don't go nuts next time. All right, now it's back to its original state. All right, good. And I'm glad you folks asked questions. We're not in any hurry, and I want to make sure that we cover things. And we're down here somewhere. Right, this one here. So again, if I can do a search, and then I search, that's what I'm here for, to explain things. So here we have a match. See, so if you can guess a few words that are in the actual thing you're looking for, you'll find it this way. So this is very much like that blind SQL injection, where you had to guess one character at a time, and You could eventually find things. It's also in the management courses like the CISSP and CISM course. There's a term for this where you use low privilege data and a large amount of it to deduce the high privilege data. An inference attack against a database is what this is. All right. And so people have used this to brute force a password from a configuration file with things like this, which is very much like what we did in blind SQL injection. Okay, good. A blur and delay. Yeah, that happens sometimes. Yes, typically you would not do this by hand. You would write a tool. Yeah. You could probably do it with burp. You could certainly do it by writing a little Python tool. And in the case of SQL injection, SQL map does it for you automatically. All right. And so another thing you can do is go to debug messages. So if you have an error thing with error messages, it'll tell you things like printing out the token and the URL being accessed. And the assumption is there's no important information in there because you can get this from your own browser anyway. But the flaw is it came from a stored container on the server side, and there's an error condition, copies it to the container, and then displays information copied from that container, and that is a race condition. It copies something to a file and then lets you view that file, which ought to be your information, but the problem is it only has one file. So if you have an error, another user might have an error in a short time afterwards, and then when you look at the condition, you'll see the other person's data. This, by the way, I heard about it maybe 10 years ago. I heard reports that there were people who would log in, I think, on their phone, and they would see somebody else's Yahoo Mail and somebody else's Gmail just sometimes. And we were never able to get to the bottom of it, but this is the sort of thing that will cause it. There's a cache somewhere that is shared, and they make the assumption that if I write it there and then show it to you, it hasn't changed in the meantime. That's a race condition. In fact, Google offered a product about 12 years ago. Google offered Wi-Fi, which was going to be more secure Wi-Fi at a time when people were using insecure Wi-Fi and it was really bad, and their Wi-Fi had some caching, and it turned out that their Wi-Fi caused this problem. One user in a coffee house would view their email, and when the next person viewed their email, it would show them the stored page with the previous person's email. And Google said, "We are obeying the official RFCs. You were not supposed to have that content cacheable." But they said, it turns out a lot of people have incorrectly designed their websites, and our standards obeying system is causing this problem, so they recalled it and quit offering their Wi-Fi service. But it's another example of the many things that can go wrong as you have many layers of servers that you're talking to, and each one of them is making assumptions, and whenever somebody does something wrong, it may contradict one of the assumptions one of the other servers made. So, all right, here's another one. If I just pull the error container repeatedly and wait for it to change, then I will get session tokens for a whole bunch of people and user input and usernames. I'm just able to harvest server-side information that should not be visible to me. So this is another problem like having error logs visible to the world, which is a fairly common mistake people make. All right, so here you have one where you have to put in several different credentials, like your username, your password, your two-factor authentication token, and so on, and they trust this thing a lot. But the bug is sometimes people log in and they get somebody else's account. Like I was saying, random and non-repeatable. They eventually found that it has to do with two people logging in at precisely the same time. And the flaw was this usual thing that causes a race condition. It stores something, typically in a temp file, and then it reads it back, and if it gets written to in between, it will change. So you log in, the thing stores your identity, then when it reads it, somebody else logged in, so you actually become someone else. All right, that's a race condition, and this is what typically happens. What you should have had was you should have stored that temporary data in something that was still part of that one user's session, so other users' temporary storage would be stored separately. But that's a little bit hard to do in older versions of Linux. Nowadays, if you look in the temp folder in a modern Linux distribution, you'll see a bunch of subfolders. Each application has its own separate subfolder to try to prevent these very common race conditions where you store something in the temp folder, and the problem is everybody can write to it. So if you want to avoid these things, see, all these are not exactly bugs. I mean, they're not exactly things a scanner will pick up. So you have to document your design, and then you have to have clear comments so people know exactly what each component is supposed to do, and then a human needs to read it with a sort of hacker mindset, thinking about how could I abuse this logical flow. Remember, there's another one that was very popular about 10 years ago. People could get in anybody's Yahoo and I think eBay accounts because you could do an eBay password reset with the last 4 of your social, and you could do something like a Yahoo reset with the last 4 of your address or something, and you could call the help desk of like a third system and get the last 4 of your socials. You could call like different companies, because this company would use one thing and they would tell you the other bit, and you could piece together these little pieces of information you could get by calling help desks to fool the other help desks and get in. The same kind of logic flaw. So anyway, you have to have clear explanation of what each stage does, and then consider ways to abuse this stuff. So you have to think how it's going to handle unexpected behavior and side effects and so on. And this is essentially how all the problems we're talking about in this course work. All right. And I didn't think of any good way to write any Kahoots about this, so there won't be any Kahoots today. But I do have a demonstration. And we're not too late, so I'll go straight into that. I'm going to